Hello, this is Chuck Ridgway, Automation Technology Manager at Horner. Thanks for joining us for another Tuesday live stream. Here's our topic for today. Using Modbus TCP and Modbus RTU in an IEC 61131 programming environment. Now, several months ago, we had a topic in which we really focused in on using Modbus in a tag-based or variable-based environment. And in that session, we looked at variable-based advanced ladder. That is the traditional American-style ladder logic programming option in Cscape that is variable-based instead of register-based. And we talked about the fact that Modbus is a register-based protocol based around a traditional PLC, and what are the implications when you're using that protocol in a variable-based environment where registers are kind of a foreign concept. Well, today we're turning our focus language-wise to the IEC 61131 programming languages, where once again, they're variable-based and registers are a foreign concept. So how can you effectively use Modbus in that situation? That's what we're focused on today. Okay, let's break down today's topic. We're going to start our program today with a quick review of Modbus. Anytime we're doing a protocol, I like to just do a 1 or 2 slide review to get us refreshed on the key points of that protocol. Included in that discussion will be the Modbus data model, another important concept to understand. We're going to talk about the traditional Modbus implementation at Horner. How has Horner typically handled Modbus? We're also going to discuss the 2 different options in Cscape for IEC 61131 programming. We have something called Standard IEC 61131 and something called Enhanced IEC 61131. How are those different? Why would you choose one over the other? And then for each of those 2 options, we're going to talk about how to implement Modbus as a server on your OCS. So if your OCS is controlling a machine and you want some of the variables in the OCS to be accessible over Modbus from a SCADA package or something similar, you'll be using Modbus in server mode in that case, and we're going to tell you how to do that. And of course, we're going to have plenty of demonstrations throughout to show you what you need to do. Let's get started. Let's do our quick review of Modbus. Remember, Modbus is the most common protocol that is used by industrial devices. So if you have an application where you've got industrial devices from multiple manufacturers and you want those to share data, Modbus is probably the protocol that is most commonly available to solve that scenario. Now, if you want to communicate serially, in other words, maybe you've got variable frequency drives or other devices whose Modbus data is available serially over RS-45 or RS-232, then you're going to use Modbus RTU or Modbus ASCII, one of the Modbus serial protocols. That is a master-slave type protocol. If you're talking about sharing data over Ethernet with multiple industrial devices, now you're talking about Modbus TCP, which is a client-server protocol. Now remember, Modbus has been around since the 70s, and because of that, it's modeled around a traditional PLC. And a traditional PLC of those days consisted of 2 different types of data: Boolean data, which is 1-bit based, and integer-based data, which is 16 bits. Now, there's 4 different types of Modbus data. You have coils, inputs, input registers, and holding registers. So coils are read-write bits, inputs are read-only bits, input registers are read-only registers, or 16-bit values, and read-write integers are holding registers. And each of those 4 different types of memory are assigned addresses. And you can see on the far right there, those are the traditional 5-digit Modbus addresses for each of those 4 data types. Now, there's also a 6-digit scheme because as PLCs have gotten larger, they have more addresses than just 10,000 per section. So there's a 6-digit scheme that's sometimes used, but frankly, the 5-digit scheme is still more common. How has Horner traditionally implemented Modbus? Now remember, the first Horner PLC has been around a while. That was in the 90s. And in those days, all PLCs were pretty much address-based, register-based or address-based, just like they were in the 70s. So with Horner PLCs, you had different types of memory. For read-write bits, we had Qs, Ms, and Ts. Remember, Qs are real-world outputs, M's are internals, but they're retained after a power cycle. T's are internals that are not retained. We also had read-only inputs, or digital inputs, %I's, which are real-world inputs. We had real-world AI's, which mapped nicely to input registers. And then we had a couple different types of read-write type integer-based data, including real-world outputs, analog outputs, AQs, and internal integer data, or %R. So those were all the Horner address types, and it just made sense to map those over to Modbus data types because they were very compatible. So when we assigned a Horner address to a specific variable, it automatically got a corresponding Modbus address through a standardized map. What did that standardized map look like? This is what it looks like. Okay, so on the left-hand column there, you can see all the traditional Horner address types, and where, in the middle column, they are mapped in Modbus 5-digit address space. And the far right column shows the 6-digit address, because again, that was created along the lines there. 3 of the 4 available logic languages in Cscape still use this map. If you're using advanced ladder, either register-based or variable-based, they still use this map. If you're using standard IEC, it still uses this map. And even though standard IEC and variable-based advanced ladder aren't purely register-based, in other words, you don't have to register map every single variable, the way they're implemented still allows this map to be used. However, this map does not apply to Enhanced IEC, and we'll show you why here in the next couple of slides. Now we're going to compare the difference between Standard IEC and Enhanced IEC, and we'll start with talking about Standard IEC. Now, Standard IEC was the first variable-based logic editor in Cscape. It predates variable-based advanced ladder. Like every other IEC package, it offers the 5 languages of ladder, structured text, etc. And again, it's been available for more than 10 years, and it's a very popular option today. We probably have, maybe 10 or 15% of our applications are using Standard IEC because it's been available a long time, and the customers who are IEC programmers, they really like it. Now, the way we implemented Standard IEC many years ago was we effectively, in Cscape, took the IEC code that was created in the application by the applications engineer, and we compile that code down into Horner runtime codes that are downloaded to the controller by Cscape and that are executed by the OCS at runtime. So at execution time, at runtime, the OCS can't really tell the difference between IEC and traditional ladder. It's just a series of codes that are executed at runtime. So that's how things work with standard IECs. Now, Enhanced IEC has only been around for a couple of years. It was released as part of 9.9 Service Pack 4. And it is a licensed feature, so it does require a very modest cost, one-time runtime license for each OCS that's executing it. Again, this is a one-time cost. It's not ongoing at all. But it offers quite a few advantages. What does it offer? Well, it offers support for 5 times as many variables. So instead of supporting 10,000 variables maximum, it supports more than 50,000 variables, so a lot more capacity. It also executes at runtime faster, and I think you'll see why here once we cover the next slide. It supports online programming. You can make programming changes and not stop the controller. For some folks, that's critical. It supports simulation, so you can test your code on your computer without having to have an OCS to run it on, at least do some level of testing, of course. It has advanced debugging tools, including the ability to do trace points. And it has very elegant exception handling. So you can provide provisions in your program in case you ever have a divide by 0, for instance. So the OCS, if it encounters that in the future and you didn't catch it in debugging, it can handle it elegantly. So it offers quite a bit, but it is quite a bit different. And one of the ways it's different is in the way it handles Modbus. But before we get to Modbus, let's talk about the way Cscape and the OCS handle Standard IEC and Enhanced IEC. So in this diagram on the left, you can see inside the dotted lines, those are the 4 different logic languages that can be used in Cscape. In any one application, you're going to select one of those 4 languages to base your logic on. Now let's focus on the 2 at the bottom. Standard IEC, you can see there, once it is created by the application engineer, Cscape then has to do a code conversion before downloading it to the OCS. And on the OCS, that download is made to the traditional Horner runtime logic engine, just like register-based and variable-based advanced ladder. However, IEC 61131 Enhanced has its own runtime logic engine that's existing on the Horner OCS. And so it can download its code directly. And so it can interact directly with the OCS firmware. And that's how we get the extra capacity, the extra performance, and some of those extra features. Now, most OCSs today have both of those runtime engines available. So the XL series from the XL4 on up, the XL Prime series, the upcoming Canvas series, the RCCs, those all support both runtime engines. However, the micro OCS does not support the enhanced IEC option. So if you're using micro OCS and you want to use IEC, you'll need to use standard IEC. So that's how execution handles and compiling happens with the 4 different options. So that hopefully will help with your understanding on how Modbus was implemented. Let's go ahead and cover a little more detail on the 2 different logic engines, okay, starting with the Horner runtime logic engine. Again, used by all the languages except for enhanced IEC. Because it utilizes the traditional logic engine, it fully supports all Horner address types. So the I's, the M's, the T's, the R's, those are all supported by the Horner runtime logic engine. And because of that, it can very easily use the traditional mapping method for Modbus server. So because T's and M's and R's exist and they can be mapped to variables, it's very simple to go ahead and map those over to Modbus addresses. However, when we talk about the enhanced IEC runtime engine, it's variable-based, and there is no Horner address support, certainly not for internals. There's no such thing as an R or an M or a T in enhanced IEC. Now, we still have I's, AI's, AQ's, etc., and S's and SR's for mapping purposes. So you can take your variables and map them over to real-world I/O and system bits and things, but that's the extent of it. So because of this, because of the fact we don't have all these Horner address types, we can't just use the Horner to Modbus map. We have to do something unique, and we'll cover that a little bit later. Now let's start with the details on how to implement Modbus server with standard IEC. Remember, it uses the standard runtime engine, so therefore it can use standard Horner to Modbus memory mapping. So the approach we're going to take here is we're going to develop our application. We're going to test it, make sure everything's working the way we want. We're going to make a list kind of on paper of the variables that we want to share over Modbus and kind of on paper create a Modbus map that we want to be able to publish to our customers. And then once we've done that, we're going to go back into our application and we're going to map those variables we want to share over Modbus to Horner R and M addresses, because once we assign the Horner R and M addresses, they will automatically have a corresponding Modbus address. So we don't map Modbus addresses directly, we map Horner addresses, and then they come through with the Modbus map. Let's say we're talking about supporting Modbus server or Modbus slave serially over RS-232 or RS-45. How do we do that? Well, we need to do that in logic. And I'm showing how to do it in ladder logic here in IEC. You could do it in structured text or one of the other languages as well. Now, to enable Modbus as a server or as a slave serial device, you need to use these 2 function codes. The first one is OpenCom. What does OpenCom do? Well, it opens the communication port that you're going to use for Modbus, say MJ1 or MJ2 or MJ3, and it sets the communication parameters. For instance, 19200 baud, no parity, 8 data bits, 1 stop bit. Now, for this function block with standard IEC, when you enter in these parameters, they need to be constants in the function block. It's looking for constants. In order to finish the details for Modbus, there's a second block required, and that's called the Modbus slave block. Now, this happens to be a block that does require you to assign it an instance, to name it just like a variable. And you need to give it a unique name. In my application, I called it MJ3_Modbus, and I made sure that was a unique name that was not shared by any other variable. And I assigned it the type of Modbus slave. So not integer, real, double integer, but go down further down the list and select Modbus slave. Now what this block does is it allows me to set the Modbus address between 1 and 252 and the Modbus timeout in milliseconds. Now for this function block, you can definitely use variables for this. So if you want your machine to have a variable Modbus address and a variable timeout in terms of how long it's willing to wait for the Modbus master to talk to it before it flags an error, then you can assign variables here. And it also allows you to assign a variable for a status variable, which of course is always important to make sure everything is working properly. So that's the setup required for Modbus Serial. What about Modbus Ethernet with Standard IEC? Well, that's handled through the hardware configuration. So you go to hardware configuration, down under the 2 LAN ports, you hit the config button for the LAN port you're configuring or enabling Modbus for. Then you click the check mark for Modbus slave. It would be more accurate if it said Modbus server, but that's the check mark you want. And then if you highlight that and press configure selected protocol, which is a button I'm not showing there on the screen, then you have the ability to go in and change some details. Although usually with Modbus TCP, the defaults are just fine. But all we've done here is enabled either Modbus Serial through code or Modbus Ethernet through configuration. How do we actually do the mapping? Well, the mechanics of doing the mapping, what I recommend you do is you go and pull up your program variable list, and then for all the variables that you want to assign as Modbus variables, in other words, you want them to be accessible over Modbus, you go to the memory column in the program variable window, and you assign them appropriate R or M Horner addresses. And again, by assigning the Horner addresses, you're assigning the Modbus addresses because they correspond through the map. Remember, if you've got 32-bit variables you're assigning, they're going to take up 2 consecutive %R variables, not just one. So you'll need to make sure that you handle that properly as well. Now it's time for our demonstration. Let's go to the bench. Okay, so here's my demo for bench purposes here. So what I've got going is I've got an XL7 here that's running Standard IEC to start. I've hooked it up to my I/O simulator. And on my I/O simulator, I've got a couple of analog pots here that are being input to simulate a pressure sensor and a level sensor. And then in logic, I'm converting that over to engineering units. And then I'm going to be assigning Horner registers or Horner addresses effectively to all the data that I want shared over Modbus. Now, in this case, it's strictly the engineering units for pressure, level, and then the set point for level. Those are the 3 things that I'm showing here on the screen. I've chosen them to all be R type data because they're all integer type data. And by assigning them to R's, I've automatically, through the built-in Horner to Modbus map, I've automatically assigned them to corresponding Modbus registers. And with our R registers, they start at 43,001. So that's what I've got going on here in my application. Now let's take a look in Cscape and take a look at how we made all this happen. So let's start with the hardware configuration. Let's go ahead and go in there and let's take a look at what we did to enable Modbus over Ethernet. So I'm going to go to the hardware configuration first, and I'm going to go here under LAN 1 because that's the port I'm using in this particular case with this XL7. And under configuration, of course, I had to configure all the normal Ethernet parameters, but then I also selected Modbus slave. And because this is standard IEC, there's really not much else to configure. I can go in here and configure selected protocol and change the defaults if I want, but in my case, the defaults are going to work just fine. So for enabling Modbus TCP as a server, it really could not be simpler. Now let's take a look at what we did to enable Modbus Serial, because I'm going to show you how to do both. So I did that in logic. So what you'll see here under my Modbus Serial area or routine in logic is I have assigned IEC ladder to this block of logic. And this is where I've got that OpenCom block and that Modbus slave block here. So that's the logic it takes to enable. And I showed this on the screen during the slide, so none of this should be really much of a surprise to you. Now let me show you how I actually went in and mapped my variables to Modbus address space. So remember, if we go back and take a quick look at our screen, we've got 3 values in this example that we want to share over Modbus. That is our engineering units, or the variable that has been converted to engineering units for pressure, level, and then the set point that we're going to go ahead and be able to change remotely. That's what we're looking to do here. So I'm going to go down to my program variable map area here, and I'm going to find the variables that were assigned for pressure, level, and my level set point. And these are the engineering units, okay? So back here, I've got a logic routine that I also wrote in IEC ladder that basically scaled my raw data from my analog inputs for my pressure and my level. But I'm not going to share all these variables. I've got multiple other variables in my application. I don't care about sharing them all over Modbus. I'm only going to share my pressure and my level, and then another one that I'm calling level set point. So down here in my program variable area, I'm going to scroll down to where those variables are listed, and then in the memory column, I'm going to assign them a Horner address. Otherwise, I wouldn't have to. And that Horner address is going to correspond to a Modbus address. So here I've got R1 for pressure, R2 for level, and my set point has been assigned to R3. And if we go back and take a quick look at our bench, we can see that on the screen here, I showed just through graphics where they're mapped in Modbus address space. Now let's go to the PC and see if we can remotely read these over Modbus and also change them. To do that, to demonstrate reading and writing Modbus, I'm going to use this utility called Modbus Poll, which runs under Windows, and I'm indeed monitoring Modbus registers 43,001, 2, and 3, and you can see the data here matches the data here. And as I make changes here, we can see the changes happening here. And for my level set point, I have the ability to change the set point remotely, and then I can see that corresponding set point change on the XL7. Okay, so that's really all there was to applying Modbus with standard IEC. It's very much like the variable based advanced ladder in terms of procedure. You utilize the Modbus map, and really it's just a matter of assigning Horner addresses to those variables that you want to share over Modbus, and then they'll automatically have corresponding Modbus addresses. Now let's pivot and talk about using Modbus Server with Enhanced IEC, because remember, it uses its own runtime engine, and therefore we cannot use the standard Modbus map with Horner registers, because Horner registers just don't really exist. So what do? Well, instead of that map, what we're going to do is we're going to create up to 4 variable arrays in our program, and one each will be used for the holding registers we want to support, the input registers we want to support, any coils we want to support, and any inputs we want to support. Now, we don't have to support all 4 types. We might only support just one, and in that scenario, we only have to create one of those arrays. However, if we want to create all 4, we create 4 arrays. And the arrays don't have to be 10,000 integers long or 10,000 bits long or anything like that. If we've only got 4 holding registers we want to share, we can make the array 4 words long. Okay, so again, we can match how much data we want to share with the size of our array. Okay, now serially in Enhanced IEC, it's very similar. We're going to do it in logic to enable serial Modbus slave. Now, we still use the OpenCom block. All right, that's the one we're going to use to, again, open or select our port, as well as to set all of our parameters like baud, stop bits, etc. But in the case of Enhanced IEC, we do have the ability to fully make everything, as far as inputs to that function block, everything can be variables. Okay, so you have a lot more flexibility in terms of allowing things to be changed at runtime without opening Cscape for changing things like baud rate, parity, etc. But it's still the same open COM block. It just has a little more capability in Enhanced IEC. Now, to finish the job and to enable all the Modbus parameters, we have a unique function block for Enhanced IEC, and that is the Modbus map slave. So this is a function block that's unique to Enhanced IEC, and this is where we again allow our Modbus address to be assigned as well as our timeout, but it's also where we specify the 4 different arrays that we've created for input bits, coils, input registers, and holding registers. That's where those are specified. In addition to, of course, providing a place for us to assign a variable for status. All right, so very similar to what we do in Standard IEC, but a little bit different. Now let's take a look at enabling the Ethernet version in Enhanced IEC. So Modbus TCP server. All right, it starts out the same. We go to hardware configuration, we press the config button for the LAN port where we're enabling Modbus server, named Modbus slave on the screen. We check that checkbox, but when we double click for the details, to configure the details, now this dialog box looks different. Now we have a place not only to select Modbus TCP or UDP and change the port number if we don't want to use the default, but we also have the ability to assign those 4 different arrays for the holding registers, input registers, coils, and inputs. Now, in terms of the length of the arrays, that is automatically assigned over there to the right. You can see a grayed out area where everything is set to 4 and 6 at the bottom. That's because Cscape will automatically read the size of the array that you've assigned to each of those 4 different Modbus data types, and it will show the size appropriately. Now, again, if you're only using holding registers, you only have to fill in the holding register array. You don't have to fill in all 4, just the ones you're actually using. So that's the configuration requirements for Modbus server with Enhanced IEC. When it comes to mapping variables, we've created these 4 arrays for each of the 4 different Modbus types. Now, to actually map the variables to Modbus, what we're really going to do is we're going to take the data in the variables we've already created in our application, say a pressure or a temperature or whatever it is that we want to share over Modbus, and then we're going to create logic, maybe in structured text, that's the one I'm showing here on the screen, that basically copies the data from those existing variables over to entries in the Modbus array, okay, of the appropriate data type. So on the screen there, you can see I used structured text assignment functions, if you will, to take a pressure and a level and to move those into the Modbus input register array that I created in my application. So that's really what we're talking about, whether it's using ladder logic and move commands or something similar, or whether it's using structured text. Now, an important note here, and that is on the bottom right, I'm showing you that I didn't just use a simple assignment function for moving variable data into holding registers. The reason I didn't is because if you have data you want assigned as a holding register, and you're truly going to allow that to be a read-write type scenario where the data could be written locally, maybe it's a set point for the PID loop or something, or it could be written remotely, maybe making an adjustment over a SCADA package of that same data, then you need to have some logic that detects whether or not that variable was changed remotely or not. And if it was, then you need to change the corresponding local variable to reflect that. So I've got a little bit of simple structured text logic shown there in the bottom right that accomplishes that. Now let's hit the bench and talk about Modbus server with Enhanced IEC. Okay, for this demo, it's very similar to what I showed for Standard IEC. I'm just showing how we would apply it for Enhanced IEC. So once again, I've got my I/O simulator. I've got my raw data coming in, simulating a pressure sensor and a level sensor here. I've got my converted data that uses logic to convert the raw data over to engineering units. Now, I mentioned in the previous demo that everything was integer data. It is integer data. So even though you see a decimal point on the screen here, that's just an implied decimal point. So the actual data in the register is 909 integer. I've just placed a decimal point there for understanding or for engineering purposes. But the raw data is still 909. And that's true both on the OCS as well as in Modbus POL, because both have the capability of putting implied decimal points into integer data. One of the differences you'll see here is, of course, there's no Horner address I've assigned. I've just shown that graphically on the screen. And I also chose to use two different areas of Modbus memory for the data that I'm sharing. So for the read-only data, the pressure and the level, I mapped those in as input registers in 30,001 and 30,002. That's just the appropriate way to do it with Enhanced IEC, because this is read-only data. And then the read-write data, I place that into the holding register area of Modbus memory, starting at 40,001. Okay, so that's what I've got going on here. Now let's take a look at the application and how I programmed all this. Okay, so we're going to start out with, instead of starting out in our hardware configuration or in our ladder section, let's start out in our program variable window, because this is where we created, and let me scroll down here, this is where we created 4 arrays or arrayed variables that represent the data that we're going to share as coils, inputs, input registers, and holding registers. So if I'm not using all 4, I don't have to create all 4, but I chose to create all 4. And then the size I created was just what I needed, okay? You know, for this demo purpose, I've got support for 4 coils, 4 input registers, and 4 holding registers. Okay, so that's what I've assigned for my application through these 4 arrays. All right, now let's go in and take a look at the Ethernet configuration through hardware. All right, so I go to hardware configuration. I go to LAN 1. Again, very similar so far to Standard IEC. I configure selected protocol. And this is where I plug in the first member of each of the 4 arrayed variables I created that represent the Modbus data. And Cscape automatically, I can't change these, Cscape automatically detected the size of those arrays and put the length for each of those Modbus variable types and set that appropriately. Okay, so again, that's all that's required for Modbus TCP server. And then let's go take a quick look at the logic routine we use to enable Modbus slave serially. So I've done that through a Modbus routine here. Okay, and again, the OpenCom block was used, but this time I chose to use variables instead of constants because I could with my OpenCom block. And then down here, using this Modbus map function block, I chose to use variables as well. And in addition to setting a variable for address, Modbus address, as well as timeout and status, this is where I assigned those 4 Modbus arrays or variable arrays that I'm using for each of the 4 Modbus data types. Okay, there we go. Now, I want to show you one thing about this function block here, and I didn't show it to you on the previous application. Okay, I had to, because this is one of the function blocks that needs a unique instance every time you use it. Okay, I needed to assign a variable or something in an entry in my variable table for mj3_modbus, which is the instance of this function block. So I'm going to scroll down here and find that mj3_modbus. There it is. And you'll notice its type is Modbus map slave. So if I double click and take a look at the list of available types, Modbus map slave is one that is available to me. So I needed to use that here as well. Okay, so I'll go ahead and just make sure I don't screw that up. There we go. And there we are. Okay, so that's enabling Modbus slave. Now let's take a look at how I moved variables that I use in my application over into these arrays that I created so that the Modbus data actually shows up where I want it. So in my application, I have a couple of different logic blocks. One is called input map and one is called output map. And my input map is the first one at the top and my output map is the last one on the bottom. Now, what I typically use input map for, and I do this in a lot of my applications, variable-based especially, and that is I'll use it to effectively map real-world data addresses over to variables I use in my program. So in this case, for my 4 digital inputs that I'm using in my example, even though I haven't shown those on the screen or anything, I assigned a limit switch, a photo eye, a proc switch, and an e-stop switch to inputs 1, 2, 3, and 4. Okay, %I 1, 2, 3, and 4. And those correspond to the built-in array, real-world I/O array that's built into Cscape that you can choose to use or not. I chose to use it here. And remember, since it's an array, it has 0 base addressing. But in addition to mapping real-world inputs, digital and analog, over to variable names, I also used it for mapping over any of my holding registers. And this is also where I would put any coil data as well. All right. And this is the scenario which I told you about, where I needed more than just simple assignment logic. I needed to have some logic which compared the current value of a specific Modbus holding register. Okay, the first one, Modbus holding register 0, or the first one which corresponds to address 40,001. And I'm checking to see if that value was changed remotely or not. If it was, then the value it was the last time on the last scan will be different or not equal than the value it was on this scan. And if that's the case, I need to take the internal variable that I'm using with that address, and I need to copy the new remote value over into that variable. Otherwise, if it hasn't been changed remotely, I'm just going to take the value of my local variable and move it over into that holding register. Okay, so that's some logic I had to create here. I chose to use structured text for a read-write variable that could be written not only locally, but also remotely. Now on the output side of things, this is where it's a lot simpler when we're mapping Modbus data that is read-only. Okay, so this is read-only, which means input bits and input registers. And for this, I can just use simple assignment logic. So I can say that for any Modbus addresses that I want to share, or variables that I want to share over Modbus, I can just use these simple assignment statements. So for each array entry, I can just map over, using assignment statements, the limit switch, photo eye, proc switch, etc. Now notice I also mapped over a motor starter and a solenoid. These are obviously outputs, physical outputs, but from a Modbus standpoint, they're read-only. Okay, I'm just going to read via Modbus the current status of the motor starter and read over Modbus the current status of the solenoid. So these are read-only. Same thing here for my pressure and my level. Those are just simple assignment statements. Okay, so that's really all it took from a logic standpoint to make everything work here. Now, one more thing I'll show you real quick, and that is here in my Modbus routine, because of the fact, if we go back to my input routine here, you remember this I wrote, this little structured text routine I wrote here. It required me, if I wanted to detect if the holding register had been written remotely or not, it required me to keep track of the last value of that holding register on the previous scan. How do I do that? Well, here in my Modbus ladder routine, I had a simple little bit of logic that basically copied over the current value of the holding registers and the input, or the coils, this scan, and copied them over into another array. And I did this at the very end. So this will represent, and I'll be using it on the next scan as what the values were the last time we came through. Okay, so I do have to do this little bit of logic to move the current values of holding registers and coils over to another array that I can compare next scan. Okay, now let's make sure everything's working properly using Modbus poll. All right, this time we're starting out just looking at our at our input registers, pressure and level. Okay, those appear to be working okay. Remember, this time we've mapped those into Modbus input registers, 30,001 and 30,002. And this is integer data. It's just got an implied decimal point I placed here using the Modbus poll software. So let's take a quick look at our OCS. And we can see we can change the data here. And if we go back and take a look at Modbus poll, we can see everything is updating as we want. Okay, now to look at holding registers, we have to open up a different configuration of Modbus pole. So let's do that now. Make sure we're connected. We are. So that's showing our set point, which is Modbus register 40,001 with a value of 5,000. And we can go back and take a quick look and verify that indeed is the set point. We can change that here. Let's change it to 6,000. Okay. We can see that it shows up on Modbus pole as 6,000. And then we can also change it from here as well. Let's say we're going to change it to 4,500. Okay. All right. Changes to 4,500. And we can verify that here. Okay. So everything worked the way we want it. So again, with Enhanced IEC, it's all about creating those arrays of data for each of the 4 different Modbus variable types or Modbus register types. It's not variables. From a Modbus perspective, remember Modbus is based on registers or addresses. Okay, so that wraps up what I wanted to show you today when you're using Modbus with Standard IEC and Enhanced IEC. And hopefully by me showing you those extra details in terms of how it's executed at runtime by the OCS through the various runtime engines, hopefully that helped your understanding a bit as to why it's handled differently between the 2 options. Okay, at this stage of the program, this is where I always remind you that we're here every Tuesday at 2 o'clock, whether we're fully live or whether we're streaming live a pre-recorded video. We've always got somebody standing by to answer questions. Please give us those in the chat section if you're watching live. If, like a lot of folks, you're watching on replay, we still want your comments and questions. Just put them in the comment section and we'll reply to those very quickly. Okay, let's talk about next week. Next week, we've got another OCS I/O themed topic for you. And what we're going to cover specifically are those flexible inputs and the rest of the built-in I/O that's included in the new OCS I/O base. It's pretty innovative and pretty useful. We think it's going to be a really good program. Okay, if you haven't done so already, why don't you subscribe to our channel? It doesn't cost anything. And if you choose notifications, you'll be notified every time we go live or every time we post a new video. And let me give you a hint. We posted a video this week. I think it was called Nate Unhinged, which is fantastic. It's pure entertainment. It's my colleague, Nate Beachy. Some outtakes from some of the recordings that he was doing for some of the videos he's been producing. It is a riot. I definitely wouldn't miss it. Way to go, Nate, to allow yourself to be kind of put out there like that. Me, myself, I'm keeping my outtakes personal at this point. Okay, so check that out. You'll have some good laughs for sure. Okay, but until next week, let's all get out there and let's do us some good.